record on this computer. Okay, so it should say somewhere that the screen's being recorded, folks. So I hope that's okay with everybody, but that lets me post these. If that's a problem, please send me an email and we'll figure out another solution for it, but it'd be really helpful if we could record these. Okay, so there, my screen's recording. We're looking at this, this particular matrix here. We're computing the eigenvalues and eigenvectors. So I just said lambda equals 2 is an eigenvalue with multiplicity 2, and we see that that's an eigenvalue because this is a triangular matrix. Now in this case, it's lower triangular, but it's still a triangular matrix. And so the determinant of this matrix is still going to be the product along the main diagonals. Just in case that still doesn't quite make sense, remember we're looking at this equation a minus lambda I and taking the determinant of that. But when we do that, we'd have 2 minus lambda, 3, 2, 1, 2 minus lambda, 4 minus lambda, and 4 minus lambda. I'm going to hold off putting in the zeros. But then if the determinant is simply the product along the diagonals, there is your determinant. And when we ask the question, what values of lambda will make this determinant 0, we can see that they are 2 and 4, each with multiplicity 2. So lambda equals 4 with multiplicity 2. Okay. Any questions about that? By the way,
I'm sorry, and it's because we know that it's the diagonal product because all the other zeros, they just cancel out the other.
I mean, it's not quite that they all cancel out. So here I did a quick look here as to why, when you have a triangular matrix, the determinant ends up just being the product along the main diagonal. And it's because of those other zeros, but it's because when you go to compute, let's say the determinant for, so if I'm expanding by minors this way, when I go to compute the determinant of D, I'm going to have a column that has all zeros in it. And whenever you've got a column of all zeros, even though I've got F and C here, when I compute this determinant, that determinant's going to be 0. And here again, when I compute the 2 by 2 minor for E, I still have this column right here of all zeros in it. And so this determinant right here is also 0. And so the only one that survives is this one. And notice because one of it's in, for the 2 by 2 case, the determinant would just be B times C minus F times 0. And so, yeah, so it is because of all the zeros, but it's not that, you can't just say that they don't just cancel them out, but when you try to do the computation, that's what you find. Yeah. Great question. Great question. Okay. So now that we've got the eigenvalues, let's go ahead and find the eigenvectors. So what do we return to find the eigenvectors? Remember, we return to this equation right here, a minus lambda I times the unknown vector that's going to be our eigenvector. We want to force it to, we want to choose the coordinates so that so the product of the two is the 0 vector. Okay. Remember, there's only one way a matrix times a vector can give you the 0 vector. That's if the vector you started with was already the 0 vector, or if this matrix right here has a determinant of 0. Okay. So let's go ahead and pick for one of our eigenvalues. Let's pick lambda equals 2, which was one of our eigenvalues. So we've got our matrix, which would be, so I'm just going to jump to a minus lambda I. That gives us 0, 0, 0, 0, 3, 0, 0, 0, 2, 0, 2, 0, 1, 0, 0, 2. That's our a minus lambda I. I'm going to join that with the 0 vector on the right there, and we're going to solve for which values of v, which coordinates of v will make that expression true. Did I do that too fast, folks? Anyone want to talk more about that?
Nope.
So again, why did this entry become 0? Because we wrote in 2 minus the choice of 2 for our lambda. And here we've got 2 minus 2. And then here, this became a 4 because we had 4 minus 2. Any questions on that, folks? Okay. So now let's go ahead and row reduce this system. Okay. Something that happens a lot more when we do this procedure than when we normally solve just any old system is that we might end up with a row of all zeros. And if you go back to our Gauss-Jordan algorithm, it said whenever you have a row of all zeros, you go ahead and move that row down to the bottom. So if I do that first, we'll have 3, 0, 0, 0, 0, 2, 0, 2, 0, 0, 1, 0, 0, 2, 0, and then that row of all zeros is now on the bottom row. Okay. I divide this row by, divide the first row by 1. To keep doing the row reduction. My next step in the row reduction is to try to get zeros in these positions here and here. So let's go ahead and do so. So for this, well, but in this case, notice I'm going to multiply this row by its opposite coefficient. When I add rows together, the only thing I do is lose that value I was hoping to lose. So I can just do that sort of without any computation. Okay. I'm going to stop the row reduction right here. Notice that this first equation corresponds to V1 is equal to 0. This second row corresponds to the equation V3 is equal to 0. And the third row corresponds to V4 is equal to 0. And notice which coordinate did not have a pivot column. I know I didn't get a 1 in this position or this position here, but you'd see those would be pivot columns. So which coordinate doesn't have a pivot column? Vector 2. So V2 is free. So what is an eigenvector associated with lambda equals 2? Well, we could do 0, 1, 0, 0 is an eigenvector for lambda. Remember, we were doing all this for lambda equals 2. By the way, then what does that make this? Let's just, instead of giving the span, let's just say that the dimension of the eigenspace for lambda equals 2 was what? What's the dimension of that eigenspace?
Is it just 1?
1.
Yeah.
It's 1 in this case. How come? Because we had an eigenvector, and any scalar multiple of that will also be an eigenvector, but no other. There's no other way to get an eigenvector from that. So this is kind of what related. This is related to what Isaac was saying when he said, if we have 2 free variables, then our eigenspace will have a basis of 2 vectors. But in this case, we had just 1 free variable. And so then any other eigenvector is just simply, instead of choosing 1, we choose 20, or we choose -5 for that free variable, but that will just give me a multiple. Uh-oh. Here it goes. Let's see here.
So the dimension is only 1 because you only have one vector, one eigenvector for that.
So careful, I have infinitely many eigenvectors, right?
Right.
So for example, 0.
Well, anything along that line.
0, 0, anything along that line. And what's the dimension of a line?
It's 1D. Yeah.
One dimensional. Yeah, because all you got to do is take this single one that we found, this one solution, but then multiply it by any scalar multiple.
But what I mean to say is we have one vector, one eigenvector, and which is linear. But if we were given, because
good. That's good to bring up linear independence. Yeah.
Right.
There are other eigenvectors, but any other eigenvector would be linearly dependent upon this. If you put any other eigenvector into a set with this one, that set would be linearly dependent.
Okay.
Yeah. So let's keep going, because I think this example actually clarifies those questions. So let's do the next step. So that was for picking lambda equals to 2. So what should we do now?
Lambda equals 4.
Pick for lambda equals 4, and let's keep going. So let's see here. I'm going to take that matrix. Let me get another picture. So let's take that matrix right here, and I'm going to subtract 4 along that main diagonal, right? So that's going to give me, when lambda is equal to 4, that's going to give me minus 2, 0, 0, 0, 3, minus 2, 0, 0, 2, 0, 0, 0, and 1, 0, 0, 0. Let me just double check that. Yes. Okay. Then that's when I put this back into the expression a minus lambda I, right? Then I want to multiply this by v1, v2, v3, v4, that vector there, in order to force the output to be 0. That's what it means to be an eigenvector. It means this times this equals this. How we doing, folks? Okay. So in this case, when we go through to row reduce this equation, let's go ahead and divide the first row by -2. And we're adjoining that with that 0 vector. Okay. Now as we do the row reduction, that'll give me 1, 0, 0, 0, 0, and then 0 minus 2, 0, 0, 0, 0, 0, 0, 0, 0, and 0, 0, 0, 0, 0. If you want, you can take one more line to get a 1 in this pivot position there, but that is indeed a pivot position, right? So the first row corresponds to the first coordinate equaling 0. The second row corresponds to the second coordinate equaling 0. The third coordinate here is free, and the fourth coordinate here is free. Okay, so this gets to the heart of this is what's challenging about these repeated eigenvalues, and so it's this example that's hopefully going to clarify it. In the first case, when we had a repeated eigenvalue, when we went to find our eigenvectors, we found that we had just one free variable, and so the eigenvectors were all scalar multiples of this one eigenvector that we picked. But now, when we go to look at our solution, here's what our solution looks like. It looks like R 0, 0, 1, 0 plus S 0, 0, 0, 1. So in this case, I've got two choices, and once I've made those two choices for the third coordinate and for the fourth coordinate, then the other two coordinates are fixed. So that means that my solution space to this system of equations here is a plane, and these are the two basis vectors 0, 0, 1, 0 and 0, 0, 0, 1 that will span that plane. So our eigenvectors, two linearly independent eigenvectors. Why are they linearly independent? Well, because this one depends on the choice of R, but notice that it only affects, there's no way you can have these two add to give you the 0 vector without both R and S being 0. So that's what makes them linearly independent. Okay, so we've got two linearly independent eigenvectors for lambda equals 4. So we could pick, let's go ahead and pick with R equal to 1 and S equal to 1. They are 0, 0, 1, 0, and 0, 0, 0, 1. So then what's our eigenspace? The eigenspace for lambda equals 4 is the span of the vectors 0, 0, 1, 0 and 0, 0, 0, 1. And so what is the dimension of the eigenspace when lambda equals 4? That's 2. Okay. So folks, this was a lot of extra work. I hope this clarified the issue of what happens when you have repeated eigenvectors. Excuse me, when you have repeated eigenvalues. In some case, nothing different happens, but in other cases, you'll have more free variables than you usually have. Generally, it's a little bit hard to say this is always true, but generally, when you have just any old eigenvalue, if it's not, if you have an eigenvalue that's not repeated, then its corresponding eigenvector will have one free variable. But the confusing part happens when you have repeated eigenvectors, repeated eigenvalues, because then you might have one eigenvector and any other eigenvector would be when you put the two together, you'd have a linearly dependent set. But it could be all the way up to, if you've got it of multiplicity 5, you could have 5 linearly independent eigenvectors for that particular eigenvalue.
Yeah, this is answer the question, because this is what I meant to ask. I just didn't ask it this way. So what I meant was, because in this case, you had 2 free variables, which means you had 2 linearly independent eigen vectors.
Very good.
Which makes it 2-dimensional. If you had 3 linear, it would be 3-dimensional, right? If you had 3 independent, okay, that's what I meant to ask.
Yeah. So whenever a space is caused by, whenever you give this, that's actually has nothing to do with. It's a good fact to review. It doesn't have to do with eigenvectors and eigenvalues per se. Whenever you've got a space and the basis is described in terms of 2 vectors, then it has dimension 2. And if those 2 vectors have to be linearly independent, and then if you add one more vector, if you no matter what vector you pick, if you add it to that set, you no longer have linear independence, then it must be what's called a maximal spanning set. And so it is that makes it a basis of that vector space. Yeah. And so remember, the dimension is always the number of linearly independent vectors that it takes to describe that space.
Is that a definition, or is that a
Yeah, great.
theorem?
You can take it as a definition, or you can take it as a theorem. So it depends on where you want to start.
Okay.
We defined a basis. We said, we gave as a definition, a basis is a set of vectors. Well, careful, let me say a finite basis. A finite basis is a set of vectors so a finite basis of a vector space V is a set of vectors V1 through Vn, so that the set is Li, set is linearly independent. So one way to look at that is there's no way to add them together and have them come out to be the 0 vector unless the choices of coefficients for those in the linear combination are all 0. So set is linear independent and it spans V. So we took that as our definition for a basis. And then you can show that that's the same thing as having if you add one more vector to it, they're no longer linearly independent. Well, I'm sorry, I've sort of forgotten your question.
I was wondering if the statement that a 2-dimensional space has 2 basis vectors, is that a theorem, like something we have to prove?
Oh no, in the finite case, that's a definition. The dimension of a space is the number of vectors in its basis, if it's a finite dimensional space.
Okay, so that's a definition then, right?
Yes, yes.
Okay, sounds good.
I misunderstood then what your question was.
Okay, I was just wondering if there was some other definition of dimension that that was more fundamental to what we were discussing here.
Yeah, there probably is another definition for dimension, but this is what we're using, and this is what most linear algebra books use at the beginning. Other questions, folks? Okay, so that was the last example I wanted to go through. So what I'd like you to do is you were asked to submit before class. You were asked to submit 6, 7, and 9, I believe. Okay. So I'd like you to go ahead and do 8 and 10. 8 and 10 are much 8 is going to take a little bit of work. 10 is going to be much easier now that we reminded ourselves that the eigenvalues are simply the products along the main diagonal of a triangular matrix. But you'll have a little bit of work to do with C. Okay. The last thing I want to talk about then is some properties of eigenvalues. So I think we started filling some of these in. And if you don't have the notes printed out, which is perfectly fine, I am recording this, and so you don't have to write out everything. Let me say that lambda is an eigenvalue of A if and only if, so this is actually just the definition, the determinant, let me make sure I'm doing the ones I want to do. If and only if the determinant of A minus lambda I is equal to 0. So that's really just the definition that we're using for an eigenvalue. Okay. Another way of saying that is that lambda is going to be an eigenvalue if when you go to solve this equation right here, folks, what goes on this right-hand side
Zero
It's vector. Yeah, zero vector.
Zero vector, right? Okay. So if that's zero, so anyway, if and only if this has what are called non-trivial solutions. Okay. Remember, if I have you solve x plus y plus z equals 0, 3x plus 2y plus z equals 0, and x minus y plus 5z equals 0. If this matrix of coefficients there is invertible, then there's only going to be one solution to this system. That's the choice where x is 0, y is 0, and z is 0. What we're saying is that we're going to have eigenvalues as long as this thing has non-trivial solutions, which is the same thing as saying that the determinant of this matrix is 0. C says A has an eigenvalue, it has a 0 eigenvalue. I think we already filled this one in. A 0 eigenvalue if and only if the determinant of A is equal to 0. That should make sense. I think you could quickly prove that right here. From this statement right here, the determinant of A minus 0 times I, well, that would be just the determinant of A. And for 0 to be an eigenvalue, then that has to come out to be 0. Okay, A and AT have the same.
You meant A minus 0 times I, right?
Yeah, is that not what I wrote?
Looks like a times, I don't know, like multiplication.
Oh, so that's an A minus, yes, and then times I. So 0 is being multiplied to the identity matrix. That's multiplication, but yeah, that was supposed to be subtraction there. And then, so A and AT have the same characteristic polynomial. Which means they're going to have the same eigenwhats, folks?
Values.
If they have the same characteristic polynomial, then the roots will be the same, so they're going to have the same eigenvalues. But they're not necessarily going to have, and generally won't have the same eigenwhats?
Vectors. Eigenvectors.
Okay. And then let's see here. If lambda is an eigenvalue of an invertible matrix, then 1 over lambda is an eigenvalue of the determinant, or sorry, of the inverse of that matrix. So if A is invertible, then finding the once you found the eigenvalues of A, you take the reciprocal of those to get the eigenvalues of A inverse. Okay, so that's all I wanted to cover on this section. So you've got, I'd now like you to submit 8 and 10. And for fun, you can try 11. I thought that was kind of an interesting question. It's based on what you would notice between the two questions that the one I've done and the one you're doing for your homework. So I'm asking you to go ahead and guess, what do you think without doing any work? What's the dimension space for lambda equals 5? And it has to do with the fact that there's that 1 there. And then this is also kind of a fun problem, but you don't have to do it. Any questions, folks, about calculating eigenvalues and calculating eigenvectors? Okay, so going forward to other questions, I will sometimes stop and we will calculate the eigenvalues and eigenvectors. And other times I'll just go ahead and have calculated them beforehand, and we'll just say these are the eigenvalues and eigenvectors, and we'll just move on. But if you ever want a refresher on how we calculate these, let me know. Usually working with a 2x2 matrix, it's not too bad, but once you get up to 3x3 matrices, it's just kind of a time-consuming process. As a reminder, you're welcome to check your answers with matrixcalculator.org, or I think Edward was saying Symbol Lab works really well too for finding those and checking your answers. So I do encourage you to check your answers. In the real world, you don't, when you're dealing with a 50x50 matrix, you're not going to calculate eigenvalues and eigenvectors by hand. So feel free to use technology to check your answers. On test questions, I'll always make them small enough that they're not too unbearable to do. Okay. I'm going to pretend that everyone's just got a bunch of names. Hope everyone's doing well. Let's move on to the next question, the next page. So this is talking about representing systems of ODEs. Okay. So pretty soon, so our goal here is to solve systems of ODEs. I actually let the cat out of the bag in class on Tuesday when I said, hey, finding eigenvalues and eigenvectors is basically all the work you have to do to solve these systems of ODEs. But we don't even really know what a system of ODEs is yet. So let's go ahead and just first look at why we would represent them in these matrix equations. So let's go ahead and the first time I'd like to do this, I'd like to represent this as 3 linear ODEs. So let's do that. We could think of X bar as being in this case, a 3x1 vector of unknown functions, x1 of t, x2 of t, and x3 of t. Or if you wanted to, you could call them x of t, y of t, and z of t. That would be another way you could do it. But usually, because we're kind of setting us up to think about having many, many equations here, we start doing subscripts as the numbers. And if that's the case, well, and we're not going to teach this in a Calc 3 class. You learn that if you want to take the derivative of a vector equation like this, or a vector function like this, you simply take the derivative of each component of it. So we're not going to do any work for that. That's material for another class. But how do I take the derivative of this? It's simply x1 prime of t, x2 prime of t, and x3 prime of t. So given that, we can go ahead and start representing this. We can kind of work backwards to the original system of equations here. So we've got x1 of t prime, x2 of t prime, and x3 of t prime is equal to -3, -2, 0, 1, 0, 0, -1, 1, 3 times our x1 of t, x2 of t, x3 of t. And then we can just go ahead and do the matrix multiplication on the right. And so we have x1 prime, x2 prime, x3 prime is equal to -3x1 minus 2x2. Then we would get x1. And for the third row, we'd have minus x1 plus x2 plus 3x3, doing that multiplication. And then what? The final step is to simply say, hey, if two vectors are equal to each other, then their components must agree. With each other. And so then we must have, for the first component, x1 prime must equal minus 3x1 minus x2. X2 prime must equal x1, and x3 prime then must equal minus x1 plus x2 plus 3x3. And there's our system. This is our 3x3 system of ODEs. By the way, one of the things that we're sort of having to cut out of this class is we've lost some time, and switching to online, everything just goes a little bit slower. Let me just give you a little bit of motivation for why we would want to solve a system of ODEs, and maybe you can think of some already. But I'd like to give you, just in terms, since you guys just studied this for your last exam, we could have tank A, tank B, and tank C, and maybe they all have their own volumes, and then maybe we've got pipes that pump water from A into B, and a pipe so that we go this way, and we might have, I'm not gonna try to draw the pipes, that's silly. We might be pumping water from A into B. We might be pumping water from B into A, and vice versa. So we might have a situation like this, and we still wanna ask, if x1 of t is the amount of salt in tank A, how can we come up with what that x1 of t is? And this would be our x2 of t, and this would be our x3 of t. So we did see, in fact, if you go back and you look at one of the homework questions very early on, I think it was our homework set 4, where we had, it was called the cascading tanks problem. But in those, it was easy to just solve one at a time because you didn't have that interconnectivity of these systems. That is, water only flowed one direction. And so you could just solve the leftmost tank, move to the right, and then move one further on. But here you've got this interconnectivity, and so it's a far more complicated problem to begin with. So that's why you would want to be able to solve a system like this.
So with partial differential equations, we're solving for a function with multiple variables. Here we're solving for multiple functions with the same variable, yes. Right?
So just be careful here, folks. We're now, so we've moved on from solving one ODE to solving for 3 ODEs simultaneously.
Okay.
So that's kind of the same thing as, when you had a system of just equations, x plus y is equal to 3. Well, there's many solutions to that one equation, but if I start throwing in a second equation, then we want the ordered pair solution, but each element in the pair is a number. For what we're doing, we're going to have an ordered pair or an ordered triplet solution, but each element is not a number, but a function. So yeah, with regards to the partial differential equations, notice that we still have, in everything we're doing in this class, we still have just one independent variable, t.
Yes. Okay.
We don't have multiple independent variables. We do have multiple dependent variables, x1, x2, and x3, but they're all dependent upon time in this case. Great. Other questions, folks? All right. So weird talking to a bunch of black boxes. All right. So the next thing I want you to do is say, what do we mean when we say that this vector right here? So our solutions are going to be vectors. Oh, thank you. We're going to say our solutions are vectors. But the vectors are themselves, each component in the vector is a function. So what do I mean when I say this vector solves the system? Okay. Well, first of all, what do we even mean by this solution here? So when I say that u bar equals e to the 2t times the vector 0, 1, 1, what am I saying when I say that that solves a system? I'm saying that these 3 functions in tandem, x1 of t equals 0, x2 of t equals e to the 2t, and x3 of t equals e to the 2t. And how did I get that? I did that by doing that multiplication, right? That would still be 0, e to the 2t, e to the 2t. These three functions all simultaneously solve this system. Okay. So if I choose to, well, in this case, this tank always stays at volume 0. This one grows exponentially this way. This one, the volume in the tank, or the amount of salt in the tank, grows exponentially in the same manner as the second one. Okay. So that's what we mean by a solution. And let's go ahead and actually verify that U is a solution to the original system. So this, here's our original system of equations written as a matrix. Let's verify that if we plug in U for our vector X, we do indeed get a solution. So we're going to check, does X prime equal A, let me say it like this, does U prime equal AU? Okay. Well, our U is 0 e to the 2t, e to the 2t. And so U prime would just be still 0 and then 2e to the 2t and then 2e to the 2t for the three components. So then we're going to plug that all into our original ODE, our system of ODEs, the matrix ODE equation. Three, 1, 1, 1, negative 1, minus 2, 0, 1, 0, 0, 3 times 0, 2e to the 2t, 2e to the 2t. So let's do that multiplication on the right-hand side. And so on the right-hand side, we'd have, for the first entry,
you multiplying it to U, or are you multiplying it to U prime?
ooh,
Yeah, that's what I was about to ask.
good catch there. That should be U.
Thanks, Christine.
Oh, me.
Yep, good. And so, yeah, because do I have a mistake here though? Sorry, folks, this should be a, I didn't get any of that right. This matrix should be -1 here, -1 here. I copied down the wrong matrix, folks. 3, 2, 1, 1, 2. So, folks, this matrix should have been 3, 2, 1 going down the first column, -1, 0, -1, and 1, 1, 2 going down, yeah, in columns. So I'm sorry about that. So if I change that over here, -3, 2, 1, -1, 0, -1, 1, 1, 2. All right, so now we'll check this multiplication on the right. So when I do this row, first row by this column, notice I get -e to the 2t plus e to the 2t, which will simplify.
3, 2, 1 or 3, 2, -1?
3, 2, 1.
3, 2, 1.
Yep. Yeah, I had to change this entry as well. I think the only number I got right was the 3 and the 0. Sorry about that.
Okay.
Hey folks, I'm sorry. We're gonna have to put a pin in this one. There's just too many things. There's too many errors in it. I think what I did was I started working one example and then brought in the solutions from another example, and there's too many errors in it. So I'm not sure. I'm not gonna try to fix it on the fly here. I think I actually have to change my U as well. So let's hold off on it. Can you see, does anyone have any questions about where we're going with what we mean by a solution to one of these equations? It's going to be a vector. Each coordinate in the vector corresponds to a function, the x1, the x2, or the x3. And then when you plug it back into the original matrix equation, you get a true statement. Okay. So I'll tell you what, let's go ahead and begin working this one that I said for you guys to check. Let's verify, because I did check this one. Let's verify that these two solutions, U and V, both solve this system. This is a little bit easier to manage anyway. So we've got U is equal to the vector 3, 2, and then V is e to the 5t times the vector minus 1, 1. And we're going to plug that into the original system, or plug each one of these in separately into the original system. Okay, so let's go ahead and do so. If I were to take U prime, what do I get for U prime, folks?
0, 0.
0, 0. Okay. And so if I plug that into the original system, we'd have, does 0, 0 equal the matrix 2, negative 3, negative 2, 3 times the vector 3, 2. And you can check this. Let's see. The first row times the first column gives me 6 minus 6. So that gives me 0. Second row times second column gives me minus 6 plus 6. So I get 0. And so, yep, that indeed checks. For our V, let's go ahead and first rewrite V this way, just to make sure that you see what's happening here. We'd have minus e to the 5t, e to the 5t. Those are the two functions, right? I'm claiming that x1 of t equals e to the, or minus e to the 5t, and x2 of t equals e to the 5t. That those two functions simultaneously solve this system. So let's check that by finding v bar prime. So that's minus 5e to the 5t and 5e to the 5t. And so then I'm going to plug both v and v bar into our original system. And when we do that, we get minus 5e to the 5t, 5e to the 5t on the left. And we're asking, does that equal what we have on the right, which is the matrix negative, or matrix 2, negative 3, negative 2, 3, times e to the minus 5t, e to the 5t. Okay. Oops. So doing the multiplication on the right, we would have 2e to the 5, let's see here.
I think you meant to put negative e to the 5t.
Yeah, thank you, Ryan. Minus e to the 5t. Great. So then let's see here. This would give me minus 2 e to the 5t minus 3e to the 5t for the first entry. And for the second entry, we would have 2e to the 5t plus 3e to the 5t. And sure enough, yep, we get a true statement there. Okay. Folks, this isn't too exciting, right? This was like way back when we first introduced ODEs. We said, hey, here's an ODE. Let's confirm it's a solution. And we took as many derivatives as we needed to, and then plugged it into the original differential equation and showed, yep, we get a true statement. That's all we're doing here. It's just a little bit more complicated because we're checking whether a vector solves the vector equation, the vector differential equation. Okay.
So right now, this process is pretty much equivalent to just taking two ODEs and checking for two solutions?
Mm-hmm.
Okay.
Now, and we're gonna shortcut some of the work that because the proofs go exactly the same, so we're not going to get to the proofs. But if we're solving a system of two equations, two functions, we've got two ODEs and two unknown functions. So I'll still call it two equations, two unknowns. We're going to need how many different vector solutions to give the general solution, if it exists? We need two different vectors, and those two vectors need to be linearly independent. So we can check to verify that these two vectors are linearly independent. What are we going to do to check to see that these vectors are linearly independent? Well, I was going to put the Wronskian. I don't think we can do that. We're going to check to see if C1 times 3, 2 plus C2 times e to the minus e to the 5t and e to the 5t, whether this ever equals the zero vector.
Sorry, why can't we use the Wronskian?
So the Wronskian is to check to see if two functions are linearly independent. But we're looking at two vectors of functions to see if they're linearly independent.
Oh, okay.
So I don't even, yes, I was thinking about, I think there's probably a higher dimensional equivalent to the Wronskian. I don't know what it is, but notice, so for example, I've got this function here and this function here, and I'd have to take both their derivatives. And then I've got this function here and this function here. That's not what we were dealing with when we were dealing with just two functions to check if they were linearly independent.
Right.
Yeah. So I think there's probably an equivalent, but I don't know it. So instead, let's go to the original definition of linear independence, which says these two vectors are going to be linearly independent if the only way you can add them together to get zero is if both these coefficients are zero. So So let's see here. The first one, if we had 3c1 minus c2 e to the 5t equals 0, then let's see, what would that have to mean? Well, let's solve this. We could solve this for c1. And if we solve this for c1, we would have c2 e to the 5t over 3 for what our c1 has to be. And then if we go ahead and plug that into the second equation, which is c1 times 2, so 2c1 plus c2 e to the 5t has to equal 0. And if we plug this in, what are we going to find? Well, that would give us 4c2 e to the 5t over 3 plus c2 e to the 5t needs to equal 0. And let's see here. That
What's that? Why is it 4c2? Shouldn't it just be 2c2?
2c2, sorry. 2c2. So folks, I'm plugging this answer into our C1. And checking this, we end up with, let's see here, this would be 2/3 C2 plus C2 times e to the 5t must equal 0. So either e to the 5t equals 0, which it never does, or 2/3 C2 plus C2 has to equal 0. And the only way that can happen is if C2 equals 0. But then that would give us that C1 also equals 0. And so these two vector functions are linearly independent. Okay.
Just to clarify, when you say vector functions, you mean a vector of functions?
Yes, yes.
Okay.
So really what I'm saying, I should be saying solution vector, and the solution vector is a vector where each, the first component corresponds to the first unknown function. Yeah.
Okay.
Yeah, thanks, Ben. Okay. So because the only way you can combine these two functions together and have it come out to be the 0 vector is if C1 and C2 are both 0, then what do we know? Our two solutions are linearly independent. Okay, so the last thing is then now that we know that we've got, and we're not going to prove this. We're just going to kind of take, but the proof would be similar. So now that we've got two different vector solutions, and we've shown that they're linearly independent, how do we give the general solution to this original system of ODEs? Well, we're going to simply write them as linear combinations of the two solutions. So this is our general solution here. And there we have our general solution to this system. Okay.
In part C of that question, it says give the fundamental matrix capital XT.
Oh yeah, so let's go ahead and do that. I didn't do that. The fundamental matrix is going to be this matrix X, which we would just represent as 3 to e to the minus 5t e to the 5t. How come? Because if I then multiply that by the unknown functions x1 and x2, that would give me, so what do I want to do? Just a second here, folks. I'm sorry, that's fine. And then if I multiply that by my unknown coefficients, C1 and C2, that's how we would have the, that's a way of representing the general solution. Sorry about that. So when you give this as a fundamental matrix, Isaac, you give the, each entry in the matrix corresponds to a function. If it's in the first row, it corresponds to x1. If it's in the second row, it corresponds to an x2. And then we multiply that by our coefficients. So that's how we get the fundamental matrix. Yeah, thank you. Oh, Evan, you have a question?
No.
Or Edward, sorry, not Evan, Edward.
Yeah, I apologize. Is it okay to take a quick bathroom break before we start the next problem?
Yeah, let's go ahead and do that, folks. Let's take let's go ahead and take 10 minutes. We'll start up here at 44. Yep. I'll just stick around and answer questions if you have them, though.
Can I ask like a very maybe broad question?
Sure.
just about linear transformations, I guess, in general. What, maybe not end goal, but what's like the direction that's headed? Like, when are linear transformations, I guess, come into play, I guess, in engineering or physics or something like that?
Hmm. So I guess the first thing I would say is we frame this course around linear transformations because it gives us the best vocabulary to talk about these problems with. But notice, you know, everything that we do with a linear, when we talk about it in frames in terms of linear transformation, there's an associated matrix with it. And I think we can see the connection between matrices and the problems that we're working on. So I think that's one answer that I can give you. Why are we doing? Because you're not going to just say, here's a linear transformation that maps you from 4 space to 5 space. But instead, what we think about it is maybe we've got we've got 3 different input values, and from those we'd like to come up with these 4 different output values. Well, then that's, if those are all linear, then that's a transformation from 3 space to 4 space. And so, you know, I think I'll just leave it at that.
Yeah, definitely.
So this fundamental matrix, what does it set equal to? So is it, so yeah, the 3, 2, e to the minus 5t, e to the 5t times c1, c2, is that what the fundamental matrix is, or is this set equal to something?
I don't know if his speakers are on.
No, they're on. I'm thinking. You know,
I just thought you were ignoring Evan.
So I'll just say, I haven't done much with the fundamental matrix. I've always given my solutions this way. And so I don't think our book uses it. Oh, it does use fundamental matrix. So I guess, if we were, so we're currently only working with a homogeneous system where we've got x prime bar is equal to ax. But if we had if this was non-homogeneous, then we'd have a separate function, a separate vector right here in this problem. So for example, maybe we had this system x1 of t is equal to x1 plus x2 plus x3 plus e to the t, and x2 of t is equal to, I don't know, minus 3x3 plus 5 e to the t, and x3 of t is equal to x1 plus x2 plus the sine of t. So we're probably not going to get into many non-homogeneous systems, but the strategies that we developed for solving non-homogeneous linear equations will carry over to the systems of equations, where we would expect a solution x of t to look like x homogeneous plus x particular. And so the x homogeneous would be our fundamental matrix. That's the fundamental matrix times the coefficients, however many you have. So it's kind of like saying, like when we said the homogeneous solution, when we were just dealing with the nth order problem, the nth order linear problem.
So is the fundamental matrix the A or the X then?
it's the x
A,
that
right?
comes
'Cause
out
X
to be.
is
So
vector.
this is the diffie-q. This is the system of differential equations. This is how we would give the solution as a sum of the homogeneous solution, and this would be represented by. So put another way, if we were solving a non-homogeneous system, maybe we'd have x of t is equal to, maybe this had a non-homogeneous system, so we have c1 3 2 plus c2 e to the minus 5t e to the 5t, and then if this were a non-homogeneous system, we'd have some other expression here. So we'd have maybe, I don't know, maybe it has a sign in it. Let's just say sine of t 1 0 minus cosine of t 0 1 0 3. This would be the homogeneous solution. This would be the non-homogeneous solution, or the particular solution to the non-homogeneous equation. And so another way of representing this homogeneous solution is to say that it's 3 2 e to the minus 5t e to the 5t times c1 c2. And that sort of is a more compact way of writing this expression right here.
Okay. So
not the most satisfactory of answers, but that's one way to think of it. Yeah.
So the fundamental matrix is just the matrix of functions, and then we multiply that by the the vector of coefficients to get the homogeneous solution.
That's correct. Yes. Okay. Yeah. So yeah, maybe. So I should have written this over here as x c1 c2. Great. Okay, folks. Is anyone? Well, they can't answer the question. Let's just run through and I ask. Isaac, are you here?
Yep.
All right, Ben, you here?
Yep.
Nina?
I'm here.
Chandler?
Yeah.
Gilbert? Might be missing Gilbert. Chris, are you here?
Yes.
Great. Cheney, are you here?
Yep.
All right. So we're waiting on Gilbert here. We'll give it another 2 minutes. Okay, folks. Oh, go ahead. Oh, Gilbert. Great. Okay. If you guys don't mind, let's go ahead and get started. These last two questions are actually the same as the first two questions on this next handout, so we'll just jump to that. So this is what I listed as the in-class work for today, solving homogeneous systems, part 1. So let's start off with A as a 2x2 matrix. And let's suppose, if e to the RT times some vector AB solves x dot or x prime equals AX, what do we know about E? Or what do we know about this solution? Okay. So this is actually very similar to how we first started off with when we solved just the standalone nth order linear homogeneous equation, where we said, hey, we think the solution to it might be e to the RT, and then we derived the characteristic equation from it. Okay. So we're going to say, hey, we think the solution might be e to the RT times some vector, and let's see under what conditions that will be true. So if we say x equals e to the RT AB, and then we differentiate that vector, we get RE to the RT AB. Then if we plug both these into the original ODE, we'd have RE to the RT AB, that's what I'm putting in place of x prime, must equal A times e to the RT AB. And then let's go ahead and subtract this. I'm going to subtract the left-hand side over. When I subtract this over to the other side, what am I left with? I'm left with the 0 vector. And I'd have the 0 vector times a e to the RT AB minus r e to the RT AB. Again, we're just supposing e to the RT times AB is a solution, and then we're going to say if that were the case, what else would be true? And we're just going to explore this. I can go ahead and I don't know if I'm going to do a line. I could rewrite this as e to the RTA times AB for that first entry. And so then notice that I've got an e to the RT as behaving like a scalar on these vectors. So I can factor it out in front. So that would give me e to the RT, and that would leave me with a times AB minus r times AB. Let me put parentheses there instead of brackets. Everyone see what I did there? I factored out an e to the RT to the left.
Yeah.
Okay. Then similarly, I've got a vector on the right-hand side of both this matrix and this scalar. And if I do a little bit of clever manipulation here, we can rewrite this as r times I times AB, and maybe you see where this is going now. Where I is the appropriate n by n identity matrix. So now I'm going to factor this vector out of this matrix statement on the right. And so what am I left with? We get A minus Ri times AB. Well, when is a vector, when is a vector equation like this going to equal 0? Well, it would equal 0 if this constant were ever equal to 0. This is true if e to the RT equals the number 0, but that's never the case. Or if A minus Ri times AB equals the 0 vector. Well, this would be true if AB equals the 0 vector, or if A minus Ri indeterminate equals 0. So for this expression right here to equal 0, either the coefficient has to be 0, the vector has to be 0, or this matrix has to be non-singular, which means it's this matrix has to be singular, which means its determinant is 0. What does all this remind you of?
Exactly what we were just doing with the lambdas?
Exactly. So for x of t equal to e to the RT times AB to be a solution, R must be an eigenvalue, and AB must be a what?
An eigenvector.
Eigenvector or 0, but it's not going to be 0, so it has to be an eigenvector.
Is that and or the eigenvalue and or?
This is and.
Thank
Great. Yeah, good check. Okay. So that gives us motivation for how we're going to go about, come on, I can't do that, shoot. That gives us motivation for how we're going to go about solving these systems. And this is kind of what I mentioned last time. So let me just go somewhere else. So let's consider this system of two ODEs. We've got two ODEs, we've got two unknown functions. And let's go ahead and give the general solution to this. Okay? In the interest of time, because I'm going slow, I'll give you the eigenvalues and eigenvectors for this. So this has an eigenvalue lambda 1. Lambda 1 would equal -1. And lambda 2 would be 3. And this has a corresponding eigenvector of 1, -2. And this would have a corresponding eigenvector of 1, 2. So here we go. What's the solution to the system? The solution to this system is x of t equals c1 e to the minus, I'm going to go ahead and write -1t times the vector 1 minus 2 plus c2 e to the 3t times the vector 1, 2. If you wanted to give what we were calling the fundamental matrix would be e to the minus t, e to the 3t, minus 2e to the minus t, and 2e to the 3t. There's the fundamental matrix for that. Okay. So in doing this work on learning how to compute eigenvalues and eigenvectors, we actually did all the heavy lifting for solving these systems.
For the fundamental, don't you also have to multiply it by C1 and C2?
Yeah, so great question. Edward, I think I was incorrect when I put the C1, C2 there. That this is the fundamental matrix, and then to give the solution is just the fundamental matrix times the C1, C2. And if you do that matrix multiplication, you'd get the same thing as what we've got right here. Okay. So the next thing I want to look at is talking about graphing these solutions. So ideally, we're going to get through 3 of these examples. We'll see. So for the first 2, I'd like to go ahead and we'll do the procedure, and then I'll summarize the steps after the first 2. Okay. Or maybe after the first 3. Okay, so here's what we're going to do. To graph the solutions, we're going to make a plane where the one axis will be our x1 of t, and the second axis will be our x2 of t. Okay. Then the first thing we put onto our phase portrait are the eigenvectors. Okay. So let's go ahead and put this eigenvector of 1, 2 on there. So that would be right here. There's the eigenvector. Now I'm not going to actually draw I'll draw the line, but I'm going to hold off from putting the arrow on there for just a second. Okay. So from this, I can extend this line through the entire phase plane. And that was for this, actually, I guess I grabbed the second one first. So that was for our V2 eigenvector. And for V1, we go out 1 and we go down 2. So let's put that on here. So this is our V2. I'm going to hold off.
That's our V1.
Oh, thank you, thank you. That's our V1, Christine. Thanks. And let's go ahead and extend that. In fact, what am I drawing here as I do that? One way to look at that is I'm drawing its eigenspace. Okay. Or the line going through that vector. Okay. Now, so I put the two eigenvectors on there. All right. Here's how I want you to think about this. Let's look at this general solution, and let's suppose C2 came out to be 0. And our initial condition on the second one came out to be, say, 1. Or let's say our, yeah. So when, what's that?
That's my dog making sounds. Hang on.
Oh, all right. So when t is 0, if the initial condition came out to be 1 here, and we didn't have this component, when t is 0, we would just be at the point 1, -2. We'd be right here. That would be our situation, right? Then as time gets larger, what happens to this expression here? As t gets large, what happens to that expression here? Well, the -1t keeps getting more and more negative. E to a negative number gets closer and closer to 0. So this point would be brought in this way. Does that make sense? If for some reason this C2 came out to be 0 and we started in this state here, where that would mean that x1 was 1 and x2 was -2, then where would we go from there? Well, as time progresses, that would just make this expression that's being multiplied to this vector smaller and smaller, bringing us in towards the origin. Is there a way we could have seen that we were going to head that direction right off the bat from that point? And the answer is yes. Let's look at the sign on the eigenvalue. It's the eigenvalue sign that says we're going to head in towards the origin there. So I'm going to then go ahead and finish out this part of the phase portrait by just putting arrows pointing in towards the origin. Like that. Okay. So that's where we said, hey, let's suppose C2 is 0 and C1 is 1, and we just started at this point right here. Let's do the sort of the same experiment, but we're going to assume that C1 is 0 and C2 is 1. And so then where would we initially start? When t is 0, we would start at the point 1, 2, meaning when I say 1, 2, folks, the way you can interpret that is at x of 0, x1 of 0 is 1, and x2 of 0 is 2. So at t equals 0, I would be at this point right here. Okay. Well, what happens then as t gets larger? So I'm looking at just this component right here. As t gets larger, this coefficient that's being multiplied to the vector gets bigger. I'm going to stay on that line. I'm going to stay in the span of that initial vector. But what's going to happen as t gets larger? I'm going to move further away. And so I'm going to go ahead and put arrows here reading out from the origin. Now, is there a way we could sort of, in our heads, rationalize that to ourselves for future problems? Yes. What was the sign on the eigenvalue? The sign on the eigenvalue was positive, and so we point away from the origin. Okay. Now, what do we continue to do as we work through these problems? Well, we say, okay, let's pick a point. Let's just pick a starting point. Figure out which way we would head from there. So if I pick, say, this starting point right here, well, what's going to happen as time progresses? As time progresses, the coordinate that says where I am along the x-axis, what's going to happen to that coordinate? It's going to get smaller and smaller. That's going to bring my x-coordinate let's see here. Sorry, as time progresses, let me say it like this. As time progresses, what happens to this expression? This expression eventually has zero impact on the behavior of this trajectory. And this, as time progresses, this vector has more and more of an impact. So as time progresses, what's this thing going to do? It's going to move in this manner. And so what we do is we just go ahead and we fill in, I wish I was using a different color there. Let's use blue. We fill in these phase trajectories here. So if I started somewhere like here, where would I go? Well, as time progresses, the black vector is not going to have much of an impact, but it's all going to be dependent on the green, so we'll move like that. And so what would we have been doing before that? Well, as time became more and more negative, it would have been the black vector that would have been dictating how we looked. And so we would have been curving along the black vector's trajectory. Okay. So there is the phase portrait for this system. Okay. All right. Let's do another example. I'd like to just jump straight into another example. All right. All right, so what are we going to do here? We're going to go ahead and find the eigenvalues. And again, I'm going to just jump straight to it. So we get lambda 1 equals 4 with a corresponding eigenvector of 1, 1. And we get lambda 2 is equal to 1 with an eigenvector of 2 minus 1. Okay, so there's a lot of new material. What's our general solution? So it's going to be C1 e to the lambda t, so e to the 4t times 1, 1, plus C2 e to the t times 2 minus 1. There's our general solution. All right, so now we're going to go ahead and sketch the phase portrait for this. So here's our x1 of t, here's our x2 of t, and we want to sketch all the solutions based on different initial conditions. So what do we do first? We go ahead and we plot our eigenvectors. So let's see here. This is the eigenvector. For the first eigenvector, it's 1, 1. So there's our eigenvector. I'm going to go ahead and put the arrow on it. Which way is the arrow pointing, folks?
Away.
Radiating away from the origin. We see that because if this, you guys can't see me covering it up. If this term weren't there and we were only looking at this term, and we started out, then we'd start out somewhere along this this line of this eigenvector. Okay, our solution would just move along that. As t gets larger, where do we go? Well, we're regardless of what C1 is, as t gets larger, the magnitude of the vector gets bigger, so we radiate away from the origin. So that's why we put the arrows going this way. Okay. Let's draw the second eigenvector, which is the vector 2, -1. So there's that vector. And what, so there's that vector. And what am I going to do with that? I'm going to put an arrow facing outwards as well. Why? Because it's got a positive eigenvalue. So if the eigenvalues are positive, you radiate that along that, when you're along that eigenvector, you radiate outwards. And if they're negative, then when you're along it, you radiate inwards. Okay. So let's suppose we start off, say, right, let's give ourselves a little room. Let's suppose we start off right here. Okay. Well, as time progresses, both these vectors are going to, so for this to happen, for us to be in this position, notice we'd have to have, I guess, we'd have to have C1 would have to be negative and C2 would have to be positive. Does that make sense? For us to be right here? Any questions on this?
Yeah, can you explain why that is? The C1 and the C2?
Yeah, so for us to be at this vector right here, we're adding together these two vectors, C1 e to the 4t plus C2 e to the t. And let's see. Oops, I'm sorry. Which one's which here? Let me get my color coordination back one more time. This was so this was our green was 1 1. So this was lambda equals 4, and this was lambda equals 1. Okay. See, Chris, I'm actually not sure why I said that. Let me think on that for a second.
Okay.
I'll get back to you next time. Let me just show you what the path will be, and then I'll give you a little bit of justification for it. But I'm not quite sure how we would know what our initial conditions were based on where which region we're in. But as time progresses, this is showing the direction, the direction of flow if we were just along the red line. This is showing the direction of flow if we were just along the green line. So we're certainly going to be either heading out, it's sort of in somewhere in this way, right? We're either going to be heading out this way or this way or this way or this way as time progresses. But as time gets even larger, which of these two terms is going to dominate which way the particle moves, or which way the point moves.
First term?
First term, because of that lambda equals 4, is eventually going to, it's like a higher rate of growth, right? So it's eventually going to dominate or dictate the direction in which we're heading. And so we're going to start heading along the path of that eigenvector as time gets larger. So if we were here, we're going to keep growing in either direction, but we're eventually going to let's see here.
Yeah, how would you draw that?
Yeah, sorry. So we keep going in either direction, right? So we'd head off maybe this way first, right? And then as time gets even larger, it's the green vector that's going to have a little bit bigger impact on where we're going. And then even time goes even further, it's going to be the green vector that has an even bigger vector or bigger impact on which way we're heading. And so what is our path then? Our path would be something like this. And if we started out, say, right here, the red vector would still have an impact for a while, but eventually that green vector would dictate the direction in which we head. Likewise, if we started out here, our direction of flow, right, we've given these arrows on it, so that's our rate of change that shows our direction of flow. So we're going to be heading in this direction somehow, right? Either here or here or here. But eventually, so they're both going to grow, but as time goes on, it's the green vector that's going to dictate where we head. And so we have something that looks like this, and then running in this direction, it's the green vector with that larger eigenvalue. So in the absolute value sense, we start heading towards infinity, right? So as time gets bigger, we know that the x of t is going to become arbitrarily large. The output value is going to become larger and larger, but they're going to be doing so they're going to be heading away from the origin, but they're going to be doing so heading along the path of the eigenvector with the greatest eigenvalue. By the way, this is an open dot here. We've got an unstable equilibrium there. And in this example here, we would have, sometimes this is shown by coloring it halfway in, we have a semi-stable equilibrium. Okay. All right, so let's do one more, and then we'll sort of have our 3 examples that we can look at.
So x1 and x2 refer to the e to the lambda t functions, right?
Yes, yes.
Okay.
So remember the x1 and x. No, let me think for just a second here. The x1 and the x2 are the solution, the values of the two dependent functions. So let's see here. So Evan, what I think what you just said was if we had our general solution is x is equal to c1 u plus c2 v. So we've got those 2 vector solutions. Where u is a combination, where u is a x1 of t, x2 of t. And v is also a x1 of t, x2 of t function. So let's look at the solution that we gave for this function. And so our solutions for x1 of t is going to be a linear combination of c1 e to the 4t plus 2c2 e to the t, where that 2 came from that component there. Our x2 of t is going to be c1 e to the 4t minus c2 e to the t.
Okay.
But
So
when
the
we
x's are what
we look at these, so let's take, for example, x1 of t.
you get if you multiply the whole equation out.
What's that?
So the x's are what you get when you multiply everything out, right?
Yes.
Okay.
Yeah. But which of these, so regardless of, like, let's say, you know, pick your initial conditions. So you get a C1 and a C2, you'll solve for those. But then as time progresses, which of these two functions takes over for x1 of t? The one with the larger eigenvalue. And same thing for x2 of t. As time progresses, which of these two functions takes over? The one with the larger eigenvalue. And so then as time progresses, we're going to start, this term right here is going to start having, for both x1 and x2, is going to start having less of an impact. And so our behavior is going to become closer and closer asymptotically to moving in the same direction as the eigenvector associated with that eigenvalue.
Okay.
So that's why, since green was with the larger eigen value.
So really this is a
Good.
So this is a three-dimensional graph, and we're just looking at it from the side.
Oh yeah. So notice. Well, no. It's not a three-dimensional graph. Time is not present on this graph, right? Look at our axes are x1 of t and x2 of t. Time isn't present on this graph. If we wanted to put time in, maybe this would be our t equals 0, and maybe here's t equals 1, and we would see time progressing this way.
Okay, so it's like a pair of parametric functions.
Yes, yeah, I think so. I think that would work.
Okay. So how is changing the C1 and C2 values reflected in this graph right here?
So if our C1 is positive, then we would be heading, and this goes to Chris's question that I'm not quite ready to, I'll answer in a little more detail next time. I'm not quite ready to answer it. But if C1 is positive, that means that we would be flowing somewhere in the, if our C1 is positive, then we would be moving in the general direction of this eigenvector here going to the right. You can't see what I'm doing. Heading in the, so as time progresses, what's going to happen? This component for x1 of t is going to keep getting more and more positive if C1 is positive. So we would be somewhere in, I believe, and I want to hold off saying this until next time.
And then the eigenvectors, those represent when one of the C1 or C2 components are 0, right?
Yeah. Yeah.
Okay.
So real quick, let me kind of run out of colors here. So in this region right here, I believe this corresponds to C1 being positive.
Okay.
And then in this region right here, that would correspond to C1 being negative. And if C1 is 0, then we're on the red line.
Okay.
And then, so the sort of, if C2 is positive, in this case, because we're multiplying, if C2 is positive, then that would correspond to being, draw the same picture. So as far as x1 is concerned, if C2 is positive, then x1 is going to continue going in this direction if C2 is positive.
Okay.
Because we want x1 to keep getting bigger if C2 is positive.
So when it's 0, that means only the other component is the only one that we're considering. And that's why it's the eigenvector for the other component.
Yes, and that's actually
Right.
how we first started putting the, that's how we actually first started, when we first drew that red eigenvector, I guess we did the green one first. When we first drew that eigenvector, we said, okay, if the other component was 0, we're just going to move back and forth along this green line. And for a positive C value, if our C value starts off positive, then we're going to start off to the right of, when I say to the right, in the positive region for x1. And we're going to continue going in further positive because the magnitude is just going to keep getting larger because our lambda is positive. Yeah. Okay. So folks, let's go ahead and, how are we doing? Oh, we're out of time. Okay. We're going to keep working on these representing systems, solving these systems. So your first batch of solving systems is going to be due Tuesday night on the WebAssign. And you won't have to deal with any complex eigenvalues or repeated eigenvalues. And that's what we're going to cover in class next time. Okay. So for right now, this procedure, you just continue this procedure of you give the general solution, and you do that by finding the eigenvalues and eigenvectors. Then you go ahead and graph the phase portrait. To do that, you plot the eigenvectors. If the eigenvalue is positive, then the arrows radiate away from the origin. If the eigenvector is, or if the eigenvalue is negative, then it's a sink towards the origin. And then you set up your flow chart your flow paths based on that. As time gets larger, let's say you have 2 positive eigenvalues. If time gets larger, the larger of the 2 eigenvalues takes over. And so you start heading in the direction of that larger eigenvalue. If both eigenvalues are negative, the same thing. The one that's larger in the absolute value sense is going to dictate how you behave. So what we didn't put on here was this very last one. Let's say these are the 2 lines formed by our eigenvectors. And let's say they're both negative. So we've got this scenario here. If this is lambda equals -5 and this is lambda equals -1, this one's going to die out more quickly as we head towards the origin. So let's say we started right here. We're going to be heading towards the origin, right? We're going to be heading towards the origin in some sort of path. We're not going to head straight in because these 2 eigenvalues are different. And so we're going to head in a way that matches the larger, that matches the larger in the absolute value sense eigenvalue. So -5 has a greater magnitude than -1. And so we're going to start as time goes along, this component is going to die out faster and we're going to head in like this. Okay. So we'll get more practice with this on Tuesday of next week. Okay. In the meantime, you guys are working on your WebAssign for finding eigenvalues and eigenvectors. Okay. So that's due on Sunday night. Let me know if you have any trouble with that. Okay. Folks, sorry, this is a lot of information. I went a little long. If you have any questions, stick around and I'll answer them as long as you've got them. Thank you.
Cool. Thank you. Can I actually ask a quick one on the arrows for this last example we did?
Yes.
They all seem to be at least headed in the initial direction towards the lambda equals 1 line. And I was wondering if there's a reason for that before they curve off and head towards the lambda equals 4 line. If that would be like an initial condition thing, or if,
Talking about this one right here, right?
yep.
Yeah. So the opposite. So here we're saying that we just said that as t gets big, it's this vector that takes over as far as the path for the,
Yep.
for the object.
Yep.
So as t gets small, which one would have, as if t is less than 1, which one of these two would have the bigger impact?
The other one.
The other one. So the closer I get to the origin, the more the other one is going to be
More it
in
affects.
the direction. So if I'm thinking about going backwards in time, and this diagram's gotten pretty cluttered, but I'm thinking about going in backwards in time, I'm going to do so in a way that mirrors the eigenvector with the smallest in the absolute value sense eigenvalue. Now, now this whole which one takes over only applies when they are both positive or both negative.
Okay.
When the easiest case in my opinion is when one is positive and one is negative, because then there's no real discussion of how big are the eigenvalues. It's just it's just as time gets larger, one of them's clearly going to 0 and one of them's clearly going to infinity. So there's no having to compare which one gets big faster or which one gets small faster.
Totally. That makes way more sense. Awesome. Thank you.
Good. Yeah. Other questions?
I'm not sure I follow your reasoning on the last graph. Why does e to the t take over e to the 4t when it's less than 1? Wouldn't it only be when it's less than 0?
Just a second here. So we've got C1 e to the negative 5t times, let's say that's vector 1, 1, plus C2 e to the negative 1t. Let's say that's the vector 1, negative 1. So as time gets large, I may have had this one wrong. So we'll go through this one next time slowly. As time gets large, which of these two vectors is going to be smaller? And that is this one here is going to become smaller as time gets large, right? So this one is kind of lingering on a little bit longer. And so if this is where, say, we started off right here, as time gets large, we're going to head in towards the one with the so this is not what I had. As time gets large, we're going to head in this way, like this, following the trajectory of the eigenvector with the smaller absolute value. So yeah, Ben, you're right. You're right. So let's say we're right here. As time gets large, this term is going to start to die out and faster than this one, and so what we'll be left with is a component, an expression that looks more like this, which puts us more on this eigenvector right here, and so we'll head in like this, and so this would be our trajectory.
But when time is negative, then the e the -5 term takes over, which is why going the other direction, it heads the other way.
Yeah, so as time is, yeah, so let's maybe not quite make it so extreme. Let's say there's time t equals 0, and we start heading in like this. As time goes negative, we're going to start heading more and more parallel with this eigenvector. Yeah.
Okay.
So folks, we'll go through this example. I put it up too fast. We'll go through that one in more detail next time. But yeah, it's a similar consideration, but not quite exactly the same when we have those, when both eigenvalues are negative. So when both are positive or both are negative, you sort of have to run through this exercise of which one takes over as time gets large, and which one, you could look the other way, which one takes over as time goes in the opposite direction. Yeah. Other questions? Yeah, Edward.
So I just went into WebAssign again, and it did it to me again. I can share my screen if you want.
Yeah, please do that. Let's see what's going on.
Oh, you have to stop yours. So hold on, don't do that if people are still writing stuff down.
Let me stop recording too. Second here. Oh, this one is recording.
Oh, I'm